So before we start today's lesson, please, do you have any questions for me? Are there any issues regarding like preparation for the exam, the final homework stuff or anything? Okay. So if there are no questions, please let me bring this up again. As I told you during our last meeting, right, I'm going to probably award credits for doing your course evaluation. So please do the course evaluations and send me proof, send me evidence that you've submitted it, right? Yeah, so that's also something important to know going into the final. Okay, and any other questions still? Any questions? Okay, then let's get on to today's work. If you check the schedule, you see that we just have 2 meetings. So after today, our last meeting will be that on Monday. So we are getting pretty close to the end of the whole semester for this class. So let me share my screen. Please, I'm sharing my screen now. If you can't see, do let me know. You're on section 5.4, right? 5.4. Last time we wrapped up on 5.3. But there's a continuation of what we did or what we saw in 5.3. So for 5.4, we are looking at the indefinite integrals and the net chain theorem. Indefinite integrals and the net chain theorem, right? So what we are just going to do here is, in summary, all that we're going to do here is, there are 2 things you're going to do. The indefinite integral thing is just your antiderivative from 4.9. It's just that we are going to learn how to use a notation, which is like the definite integral thing. Similar, right? A notation for the antiderivatives. You're just using a notation for antiderivatives. That's what you see here, right? You're just going to use notation for antiderivative, derive a notation for antiderivative, but it's the same antiderivative that you did in 4.9, right? And then the second part is you are just going to acknowledge something that we formulated in FTC part 2. Okay, so let's get on with it. Now for indefinite integral. So we said in 5.3, we established 2 parts of a fundamental theorem of calculus. We looked at the derivative of functions which go like this. And then we said that when you want to find a definite integral, it's just the antiderivative valued at the upper limit minus the antiderivative valued at the lower limit, right? So now that we know that the definite integral, right, relates to the antiderivatives, we said that, okay, they decided that since we don't have a notation for antiderivatives, let's just use this symbol, elongated s, without the limits of integration. So once more I stress, without the limit of integration, right? So if you take away the limit of integration, then they are saying that let that denote the antiderivative. So if you see a symbol like this, right, the elongated s with some function f of x, the integrand, the x, then what it's asking you is kind of like find the antiderivative. That's all there is to it. But this time when it's attached, you can also call it an indefinite integral, right? Instead of calling like the antiderivative, we refer to it as an indefinite integral so that it relates to like the symbol. But as I said, it's nothing new. It's the same antiderivatives, right, that you did in 4.9. Yeah. But this time without limits of integration, a and b, right? The a and b are not present. So whenever you see that, think about finding the antiderivative of the integrand, right? That's all for the first part of this. So this is what we're establishing here, right? So we introduce a new notation for antiderivatives. The elongated s and then f of x dx means what? Find the antiderivative of what? Of this integrand. So for definite integral, yesterday I said that when you do the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit, the c's will always cancel out. So we don't bother bringing a c. However, remember that if you are trying to find antiderivative, you need a general solution. It will be a family of solutions unless they specify, they give you some initial conditions, right? So for this case, if this is there, right, without the limits of integration, and then you're asked to find this or evaluate this, then the antiderivative that you get should have the c. It must have the c. This because this one you're not evaluating from upper limit to lower limit of integration. You see, you're not going to evaluate it, right? So for this one, please don't forget your c, right? And the way to prove that you did it right, as you know, for antiderivatives, how you know you did it right is when you get the antiderivative, when you differentiate the antiderivative, you should get the function, right? The integrand, right? So for example, looking at s squared, what is the antiderivative of s squared? It's s cubed over 3 plus c. Why? Because if we want to be 100% sure, we can just differentiate this s cubed over 3 plus c and then get back s squared. So that's one way to check, right? So please note that this is what? Going to be a family of functions. It's a family of functions. Yeah, please, any questions so far? Okay. Now, this is just cautioning us that we should be careful, right? The definite integral is a number. It's a number, right? And for that one, the only difference between a definite integral and the indefinite integral is that for the definite integral, it has limits of integration. For indefinite integral, it doesn't have limits of integration, right? It will be, the solution will be a family of functions or a single function. It's not going to be what? A number. It's going to be a family of functions or a single function. For definite integral, it's a number, right? Yeah. And then relating this indefinite integral to the definite integral in this line, we can say, okay, whenever you are doing like the definite integral from a to b of f of s dx, then the notation is the same as writing. We know that for definite integral, a b f of x dx is just what? The antiderivative, like so, and then evaluated at what? The lower to upper, right? So that you get what? F of b minus f of a. So this notation is just saying that this, since we've now declared that this symbol represents what? This symbol represents f of x, then the definite integral can also be written like this. You see, where the f of x is the antiderivative, the definite integral can be represented like this, right? Similar to what we have here. Please, are you okay so far? Any questions? Anybody needs time on the slide? Okay. Okay, so now let's look at one simple example. So for instance, when you have this symbol, the elongated s and then secant squared dx, then all that we are asked to find is what? Just the antiderivative of this. So the question is, what's the antiderivative of secant squared dx? Well, we say, okay, when we differentiate tan, you get secant squared. So the antiderivative is tan of x. But please don't forget your arbitrary constant, so plus c. Now, to verify that this is indeed right, we can try and differentiate this side, the tan of x plus c. And when you differentiate it with respect to s, you get secant squared, which is the integrand. So that confirms or validates what we had, right? Okay. So all the table, please try and remember, look at the tables, the antiderivative tables, right? They will be very important, right? So that's the long list, right? Yeah. Okay. You're not responsible for the SANCH, the hyperbolic function. So let me circle them. This one, this one. But this is also not exhaustive. This list is not exhaustive. The exhaustive list is what we did in 4.9, right? So not responsible for these. For these. Yeah. Okay. Please, any questions on this? Okay. Then let's try some examples. So example one, for this one, let's do this together. So solution. So the first thing we notice is this one says find the general indefinite integral, right? And then we have the elongated s without limits of integration. So that should tell us that, okay, for this one, the question wants us to obtain like an antiderivative of the integrand. So I go, okay, 10x to the power 4, 2 secant squared of x, and then dx. Okay, so let me try and find the antiderivative of the integrand. So for the first part, 10 is a constant, ignore. And then for s to the power 4, we use the power rule for antiderivative. So add 1 to the power, divide by the result, right? And then minus, for the secant squared, we already saw that the antiderivative of secant squared is tan, right? So that's just tangent of x, right? But please, when you get here, you're not done, right? This is not a definite integral. It's not going to be a number. So please, you must add your what? Your c. So simplifying things, 4 plus 1 is 5. 5 goes into 10 two times. So you have 2s to the power 5. And then minus 2 tangent of x, right? 2 tan x, and then plus c. And that will be a what? A solution. Please, are you okay with this? Anybody needs time here? Okay, then please try this one. Let me give you like some seconds to try it. Right, so please try it. When you're done, you can just voice your answer. Voice out your answer. You can send it via chat too. That also works. So please try this. So we have some space. So. Okay. I was just checking the space. Any possible answers? Okay, I see something in the chat. You cannot change cosine the quote. Okay, can we change cosine the cotangent? Yes, that's a good idea. Yeah, you can do that. So you see, the thing is, when the integrand, you can change cosine over sine to cotangent. Yeah, when the integrand does not look directly like something that you can get the antiderivative, sometimes you have to do some manipulation of the integrand before you can get the antiderivative, you see. So maybe it doesn't stand out directly that cosine of theta over sine squared theta has an antiderivative, but maybe you can do some manipulations and make it look like something you can get an antiderivative of. Yes, anybody? Okay. Or I should give you time. If you are working this, you're almost there, let me know. Okay. Okay, let's do it together. So for this one, I start. This one wants the indefinite integral. So the question is, do I have a direct antiderivative for cosine of theta over sine squared theta? Nothing comes to mind, right? But I say, okay, cosine of theta over sine squared theta is the same as cosine of theta over sine of theta times 1 over sine of theta, and then the theta. But then cosine of theta over sine of theta, as you said, right, is cotangent, right? It's cotangent of theta. And then 1 over sine of theta is going to be what? 1 over sine of theta is going to be cosecant of theta, d theta. And then the question is, what is the antiderivative of cosecant theta, cotangent theta, right? Now, we know that the derivative of cosecant of x is what? Negative cosecant cotangent. So without this, you're going to say this is what? Negative cosecant of theta plus c, because that's the standard rule for this, right? Because the derivative of, so note on the side, so note that the derivative of cosecant of x dx is what? Is negative cosecant x cotangent x, right? Cosecant x cotangent x. You see, so if this is positive, then that means it was the derivative of a negative cosecant of x. You see, so that's it. We are done. That's our answer. So the answer is provided here, right? So it did exactly the same thing, right? So the lesson here is sometimes if it's not direct, you have to simplify or manipulate the integrand before you can get the antiderivative, right? Okay, so like so, and then we get this. Okay, please, any questions here? Okay. Anybody needs time on this slide? Okay. Okay, then let's move on. So now what about this? For this one, we have to be cautious. This question is not asking about the indefinite integral. This is a definite integral. You see, this is a definite integral. For this one, I'll do it on a whiteboard since it has the solution here. So I just do it on a whiteboard. So for this, let's proceed to the whiteboard. So this, you're on 5.4. And then you're looking at example 3. Example 3 on slides. Okay, so you're trying to do integral from 1 to 9, 2t squared plus t squared square root of t minus 1 all over t squared dt, right? So this one, you're going to use the fundamental theorem of calculus part 2, right? Whenever you want to find a definite integral, just find the antiderivative of the integrand and evaluate at the upper limit minus evaluated at the lower limit. So starting from the fact that we can't identify a direct antiderivative, I know that I'll have to manipulate the integrand a little bit and then try and see if I can get the antiderivative. So this is what I'm going to do. So I'll go 2t squared over t squared and then plus t squared and this times t to the half. Let me write it as t to the half so that I can use the power rule when I want to find the antiderivative. And this t to the negative 2, right? And then dt. I still bring the same elongated as 1 to 9 because I've not yet found the antiderivative of the integrand. I'm just manipulating the integrand, right? So at this point, t squares cancel out and I have 2, and then, so bring the 1 to 9. And then for this side, the t squares also cancel out. I have t to the half and then minus, this is just t to the negative 2 dt, right? And now you can clearly see that this original integrand was continuous or is continuous on this interval, right? The continuity assumption is satisfied. So FTC part 2 can be used, right? So right from here, I say, okay, what is the antiderivative of this integrand that I have here? What is the antiderivative, right? So I go for 2, it's just 2t. For t to the half, that one I can use the power rule. So that's t half plus 1 over half plus 1. For the minus 2, this power is not negative 1. It is not negative 1. So I can still use the same process, right? Just add 1, the power rule for the antiderivative, and then divide by the result. And then now that I found the antiderivative, I won't bring the elongated s again, right? We keep writing the elongated s when we've not taken the antiderivative yet, right? But after we get the antiderivative, please do this, right? So that we know that we are now going to evaluate this at the upper limit minus what? Evaluated at the lower limit, right? So that you know that you've already gotten your antiderivative. As long as I keep repeating this, I know I've not obtained my antiderivative results yet. Okay, now I think we can simplify this a bit, right? So that's just 2t, and then the half plus 1 is 3 over 2. So simplifying that, we get 2 over 3, and then t to the 3 over 2. And then this one, the minus 2 plus 1 is negative 1. So the negatives will cancel out, giving us a plus, and then t to the negative 1. And this evaluated from 1 to 9, right? And then when you get to this point, you just evaluate it at the upper limit. So that's 2 times 9. Wherever we see t, we plug in 9, right? 2 over 3, and then 9 to the what? 3 over 2, and then plus what? 9 to the negative 1 is the same as 1 over 9, right? And then minus, you plug in 1. So that'll be 2 times 1, and then plus 2 over 3, and then 1 to the 3 over 2, and then plus what? 1 to the negative 1, which is 1 divided by 1, which is 1, right? So now it's just either you simplify or you just simplify this, right? So simplify. So here we have 18. I think we have 18 here. And then for this one, 9 to the 3 over 2, 9 to the 2 over 9 to the 3 over 2. 9 to the 3 over 2 is the same as what? 3 squared to the 3 over 2, which is equal to the 2 to cancel out. So that will be 3 to the 3, and 3 to the 3 is 27, right? So we get 18 plus 20, 2 over 3 times 27, and then plus 1 over 9, and then minus. For this, 2 times 1 is 2, and then 2 over 3, and then 1 to the 3 over 2. That's minus 2 over 3, and then we have minus 1. Right, so when you get here, just group like terms. I see this, I see that, I see this one. I can group these. So what do I have? That'll be 16 and then 15. So 15 cleared. And then for these two, I have plus 22 over 3 times 26. For these two, I've dealt with these two. And then plus 1 over 9. Right, and then for this, I can just say, okay, 15 plus, okay, so let me just add these. So I have 15, and then plus, I have 2 over 2 times 3, and then 26 over 9 plus 1 over 9, right? So 2 times 3 times 26, right? 2, 3 is 6, and then 6 times 26, that's 120 plus 36, that's 156. So 156 plus 1, 156 over 9 plus 1 over 9 plus 15, right? So that's just going to be 15 plus, what do you call this one? 157, 157 over 9, right? So everything simplifies to, well, for this math, I mean, for this calculation, when you get here, you can do whatever works for you to get your result, right? So, or to simplify your answer. So in the long run, we have this integral 1 to 9, 2t squared plus t squared square root of t minus 1 over t squared dt. This is finally equal to, so I have 15 plus 157, 15 plus 157 over 9, right? So 15, you can still simplify if you want. 9 times 15 plus 157 over 9, right? So that is going to give you 9 times 15 is 90 plus 45, which is 135, right? So 135 plus 157 over 9, and that'll just be so 200, 235, 285, and then 285 plus 7, that's 327, I guess, over 9. Yeah, 285 plus 7, 5. No, it's wait. 285 plus 235, 285, 285 plus 7. That'd be 5. No. So that's incorrect. Yeah. So 285 plus 7 will be 5 more. That's 290, and then 292. Yeah, that's more better. Yeah, that's more like it. Yeah, so this is what you're going to get. All right. But there is an answer actually on the slides, which we can easily compare to, but that's the result. Please, any questions on this? Hope you're okay. So when you write this as a mixed fraction, I think you get like 32 and then something over 9, 32 and something over 9. Yeah. Okay, so let me go back here. We have the solution here, which we can compare this to, right? So the key is get the antiderivative. This is a definite integral, evaluated at the upper limit minus evaluated at the lower limit, right? So you get this, you do the math, and you get this. Yeah, so yeah, you get 32 4 over 9. So you can cross-check with the answer that we had. Okay, please, any questions so far? Okay. So now let's go on to applications. Well, for this one, we just want to establish a rule using the fundamental theorem of calculus part 2, right? So from the fundamental theorem of calculus part 2, we said that when you want to evaluate a definite integral, it's just the antiderivative evaluated at the upper limit minus antiderivative evaluated at the lower limit. Now, remember that this indefinite integral is the same as what? The antiderivatives, the derivative of the antiderivative. So writing this in this form, right? Writing the first integral, the first definite integral in the form where we have the derivative of the antiderivative, you can see this representation that the integral from a to b of what? The derivative of the antiderivative is going to be what? The change, right, in the antiderivative at the upper limit minus what? The antiderivative at the lower limit. So all that we are trying to say is, right, the definite integral over a region is going to be a change in the original f, right? So the definite integral of the derivative is going to be the change in the original function. That's all, right? So it's just a change. So this one is saying, so f prime of s represents the rate of change of uppercase f of x, right? And then this f of b minus f of a is a change in y when s changes from a to b. So from what we established, we've been able to say that this f of b minus f of a is just going to be what? Equal to what? The definite integral, right? Of where the integrand is the derivative. So this f of b minus f of a represents something we call a net change in y. It's a net change, right? You see this depending on the field that you are. For instance, when you go on to physics, right? In physics, you do a lot more of this in relation to like position functions and velocity, right? So the theorem says the integral of a rate of change is the net change, right? That's what you're saying. That's the net change theorem, right? So whenever you are integrating a net of change over a region, it's just going to be what? The net change in the function, in the original function, not its derivative, in the original function, right? So this principle can be applied to several fields, as I was telling you earlier on, right? So depending on the area that you are, this may ring like click, depending on where you are, right? So if it's volume, you encounter volume, V of t is the volume of water in a reservoir time t. And then V prime of t is the rate at which the water flows into the reservoir time t, right? Then if you are asked to evaluate what? The definite integral from t1 to t2 of V prime of t, then we say, okay, this one is a rate of change. So if we are looking at the definite integral of a rate of change, then it's just a net change, right? So that'll be V of t2 minus V of t sub 1, right? So that'll be what? The net change with the amount is a change in the amount of water in the reservoir between T1 and T2, right? Well, we can also have C of T, right, to be a concentration of the product of a chemical reaction. So if you are maybe a chemistry student, this may make sense, right? And then we are saying that the rate of reaction is the derivative, dC over dt, right? So if that's the rate of change, which we have here, and then we are integrating over a region, right, T1 to T2, then the result is what? It's a net change in the original concentration of the product of the chemical reaction time at T. It will be a net change, right? So that's the change in the concentration of C1, of C from time T1 to T2. Maybe you're also modeling something where you'll be using the mass of a rod measured from the left endpoint to a point, right? So you see the derivative cuts across fields, right? Integration and differentiation cuts across fields. Okay, so for this one, we are saying rho of x is the derivative, right? M prime of x, where M of x is the mass of the rod measured from the left endpoint, from the end to a point x, right? Then the definite integral from a to b of this rho x, don't forget rho x is a derivative, then it's just going to be what? A net change. So it's just going to be the original function m evaluated at the upper limit minus what? The original function evaluated at the lower limit, right? Now, maybe all that we've talked about doesn't still make sense in your field. You've been thinking about your field, it still doesn't make sense. But who knows? Maybe you're into population. Your field deals with population, right? So for population 2, it also applies there, right? So the rate of growth of a population, let's call it dn over dt, right? Then this integral from t1 to t2 of dn over dt of a rate of change is just going to be what? The net change in the original function n of t, right? So it's just going to be the net change in population during the time period. Okay. Please, any questions so far? Okay. Next, maybe you are also into something of production, right? So C of X is the cost of producing X units of commodity. Then the marginal cost is the derivative. So if you're asked to evaluate what from X1 to S2, that's the units, right? The units of the commodity that's produced, of the derivative or of the marginal cost, then it's just going to be the net change, right? So that'll be the cost at the X2 minus the cost at the X sub 1 units produced, right? Still, maybe you're into physics, right? Then you know that the velocity is the derivative of the position function. So if you're asked to evaluate this definite integral from time t1 to t2 of a velocity, then you know that it's going to be a net change in the position function. You see, right? So the net change. So the position function evaluated at the upper limit minus the position function evaluated at the lower limit. Okay. Now, let's look at some other applications. So we are looking at the velocity and an acceleration, velocity, right? Velocity and position function. So now, suppose we want to calculate the distance of an object, right? The distance that an object travels during a time interval. Now, remember that velocity is a vector quantity, right? It's a vector quantity. It has both magnitude and then direction, right? When it's moving in the positive direction, then the velocity is positive. When it's moving in the negative direction, the velocity is negative. So if we want to compute, say, the total distance travel, right? The total distance travel. Because velocity can be negative, we cannot have negative distance, right? Distance, on the other hand, is a scalar quantity. Distance doesn't have direction, right? So if you want to compute this using the net change theorem, then you have to work with what? The absolute value of the velocity, so that for the places where the velocity is negative, we can calculate this distance that the velocity covered by getting the absolute value. So when it was negative, we apply the absolute value on that negative velocity and get a positive velocity, so that when we integrate, you get a total distance traveled. Right. So I'll do an example of integrating absolute values for you to see. Right. So this is a good graph of what is happening. Right. So the corresponding vector quantity of relating to distance is displacement. Displacement is a vector quantity. It has both magnitude and direction. So for that one, if you want to get the displacement over a time interval, we don't do the absolute value of the velocity. We just maintain the same velocity function, right? And that one will be what? To be a difference in areas, right? It will be a difference in areas, right? So we have A1 minus A2 over A3. That's this is the diagram representing the velocity function. See this part, the A2 is the negative, A1 is positive, A3 is positive. So when you do this definite integral, you end up adding the A1 and A3 and then subtracting the A2. On the other hand, distance cannot be negative, right? So even for parts of A2, which is negative, we have to, when we take the absolute value and take the integral, right? The absolute value will make this positive so that we can get the total distance to be A1, A2, and then A3 all added together. Okay. Now, you also know that we learned in a previous chapter that acceleration is the derivative of the velocity, right? So that means that if the question asks you to evaluate the definite integral from a time t1 to t2 of acceleration, there is going to be what? The net change in the functions whose derivative is the acceleration. And that is what the velocity evaluated at t2 minus the velocity evaluated at t1. Please, any questions so far? Anybody needs time to catch up? This was just talking about the theory where you can apply it. So yeah. Okay, if there are no questions, then let's proceed with example 4, which will be the last example, right? So for part A, it says find the displacement of the particle during a time period 1 to 4, right? So we are given the velocity function. We have to find the displacement. So let me do that on a whiteboard. So this is example 4. Example 4 on slides. Okay, so for this one, we have the velocity to be equal to t squared minus t minus 6, right? So for part A, if we want the displacement, part A is displacement, right? So displacement over the time period 1 to 4, right? So over the time period 1 to 4. So let's do this. Now we know that for displacement, all that we have to do is what? Is to do the definite integral from 1 to 4, so elongated as 1 to 4, and then of the velocity. That's all we have to do. That will give us the displacement, right? So that'll just be 1 to 4 t squared minus t minus 6 dt, right? So with this one, all that you have to do is just get, this is a definite integral. So this function is continuous on the interval. So just get the antiderivative, evaluated at upper limit minus evaluated at the lower limit. So we go, okay, so that one, the first one is t cubed over 3. And then the next one is t squared over 2. And then the next one is 6t. And then you're evaluating from 1 to 4. So when you get here, you can just plug in the upper limit. So that'll be 4 cubed over 3 minus 4 squared over 2. And then minus 6 times 4. Right, not 64, 6 times 4. And then minus, plug in the lower limit. So that'll be 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. Right. So when you evaluate everything here, you're going to get, I think, negative 9 over 2. Right, so your final answer is negative 9 over 2. So this is what? Our displacement. And we are done. Please, any questions on the process? So it's just what we've been doing, but this time we are just applying. It's an application, right? So that's all. Any questions here? Anybody needs more time here? Okay. Okay, then let me shift to the PowerPoint. So the second part says find the distance, travel during this time. Find the distance, travel during the same time interval. Okay, so the lesson that I want you to take from here is you will not be actually tested on applications, but you may see a question where you may encounter a case where you have to do a definite integral of an absolute value function, right? So here is where I teach you that how to do the definite integral of an absolute value integrand, right? Or with an absolute value integrand. So now for this one, we are looking at the distance from 1 to 4 still. So based on what we saw, the formula that we said you use for the calculation of a distance when the velocity is given is what? Just do the interval, so 1 to 4. But this time we do absolute value of the velocity, dt. So that means for this problem, you're looking at 1 to 4, absolute value of what's the velocity function? Is t squared minus t minus 6 dt. Right, so when you get here, the thing is, for this part, right, we cannot get the antiderivative directly because this expression here, this thing that you see here, is an absolute value. How do you get the antiderivative of an absolute value? You can't directly do it. So what can you do? Well, one thing that you have to observe is the absolute value function. Let's break it down. We can break it down into parts where it's only positive and parts where it's only negative, right? So recall that when you have absolute value of x, then it's just going to be what? X if x is greater than or equal to 0, right? And negative x if x is what? Is less than 0, right? We saw this previously. So that means that similar to what we had for the absolute value of s, for absolute value of t squared minus t minus 6, we just have to figure out, we know that it's going to be what? T squared, the same thing, t squared minus t minus 6 for something, right? And it's going to be the negative of the t squared minus t minus 6 for some other condition. So all that we have to do is within the interval 1 to 4, right? Within the interval 1 to 4, we have to figure out which side the function is positive and which side the function is negative. Right? So how do you do this? So from Math 126, you learned how to do this, right? So if you have t squared minus t minus 6, how can you tell which side is positive and which side is negative? Well, you set it equal to 0, right? When you set it equal to 0, you find the factors, right? So for this one, I have t minus 3, t plus 2. So that's equal to 0. When I solve for these for the zeros, I get t equal to 3 or negative 2. So what I'm going to do is I'm going to partition, right, the whole space using these points, right? So for t equal to negative 2, it is on this side. And then say for t equal to 3 somewhere here, right? But the thing is, this definite integral that we are looking at, the interval is from 1 to 4. It doesn't include the negative 2. So you can kind of like cut this off, right? And focus on only this interval. So now for this interval, let's test. Is for this side, right? For the 1 to 3, is the t squared minus t minus 6, is it positive in this region or negative? Well, let's pick a number in between the 1 and 3. So you pick a number, say 2, right? And then you plug it in the t squared. So when t equal to 2, right? What is this going to be? What is t squared minus t minus 6 going to be? Well, that one is going to be 2 minus 3, right? And then 2 plus 2, right? This one is going to be what? T squared minus t minus 6 is, this one is what? 2 minus 3 is negative, and then 2 plus 2 is positive. Negative times positive is negative, right? It's negative. So that means for this side, for this interval 1 to 3, this is negative. Oh, what did I write? Not positive. This is negative. The function is negative. Now, let's pick a number between 3 and 4. So say 3.5, right? 3.5. When t equal to 3.5, well, what is t squared minus t minus 6? Well, the factored form is easier to use, right? So let's see. So that'll be 3.5 minus 3, and then 3.5 plus 2. So this will be positive and then positive, right? So t squared minus t minus 6. For that interval 3 to 4, we know that this is what? Is positive, right? So positive. So using this, right, we can say, okay, we know that for this interval 1 to 3, the function t squared minus t minus 6 will be negative. So that means for the condition that we're looking for down here, we are going to say t squared minus t minus 6 is negative for what interval? It's negative from 1 to 3. Right? It's negative from 1 to 3. And then for the positive part is going to be what? From what? 3 to 4. Like so. So that we get the intervals. So please, any questions up to this point? I know this is a bit foreign. It depends on your knowledge from 126, but I hope it rings a bell. It looks familiar. You've done stuff like this before, right? Okay, but please, do you need time here? Anybody needs time? Or is there any part you want me to explain again? If you don't get anything, feel free to let me know. Right. So we are trying to, the goal is we are trying to take away the absolute value symbol, right? And you know that when you write the absolute value symbol, you break it down into these pieces. They will no longer have absolute value. For example, absolute value of s, if I write it as either x or negative s, the absolute value goes away, right? So absolute value of t squared minus t minus 6, if I write it as either t squared minus t minus 6 or negative of that, the absolute value has gone away, and I can get the antiderivative of those. So that's the motivation why I'm breaking this down. Right. Okay. So if you don't need time, let me proceed. So now I'm here 1 to 4, and then absolute value of t squared minus t minus 6 dt. So remember that we said that. So note, let me use a different color here. So note, do you recall we said that for the properties of definite integral, we said integral of from a to b of f of x ds is equal to what? Integral from what? A to c of f of x ds plus integral from what? C to b of f of x ds, if the c is in between the a and b. Do you remember this property? Right. So based on this property, I can say, okay, now for this 1 to 4, I can break it down into integral from 1 to 3. Right. Where am I using? Why am I getting the 3? Well, it's from here, because I know that when I break it down at 3, I can get parts, intervals where the function is only positive and the intervals where the function is only negative. So I'll do from 1 to 3 and then 3 to 4. Right. So I'll do from 1 to 3 of this function. And then plus what? From 3 to 4 of the same function. Based on that property of definite integrals. Right. Please, I hope you're okay. Any questions so far? Okay. But then the thing is, for this interval 1 to 3, we know that the absolute value of t squared minus t minus 6 is what? It's negative. So that means that for absolute value of t squared minus t minus 6, you have to write what? Negative and then t squared minus t minus 6. You see, so that becomes integrate from 1 to 3. The absolute value now, we can take away the absolute value because it's strictly negative on this interval. So you want to negate that. And then plus 3 to 4. And then for this interval 2, the motivation for breaking it down is so that this absolute value is strictly positive on this interval. So if it's positive, what does the absolute value becomes? We just write the same expression inside the absolute value. So that's t squared minus t minus 6. So we get what? T squared minus t minus 6 dt. Right. Now we've been able to take care of the absolute values. We have just functions we can get the antiderivative of. Right. So we take the antiderivatives. So for this side, let me distribute the negative through. So I have minus t squared plus t plus 6, and then dt, and then plus 3 to 4. This is still just t squared minus t minus 6 dt. See, now we can get the antiderivatives because it doesn't involve absolute values again. So you're going to get negative t cubed over 3, and then plus what? T squared over 2 plus 6t right? And then you evaluate this from 1 to 3. And then for the second piece, you have t cubed over 3, and then minus t squared over 2, minus 6t. Then that one to evaluate from 3 to 4, right? So when you get here, it's a matter of plugging in and evaluating, right? So this is going to be, I'm going to write this and then do negative t cubed over 3 plus t squared over 2 plus 6 times 3, and then minus what? So you plug in you plug in 1, right? So that'd be negative 1 cubed over 3, and then plus what? 1 squared. I probably need more space. Please, guys, let me take it to the next slide. Right? Sorry, let me take this to the next slide. I'll need more space on this. But please do let me know if you need like time here. I hope it makes sense, right? Is there any part that is confusing you? Do let me know. Okay. So we have 1 to 4 absolute value t squared minus t minus 6 dt. It's going to be what? So I'm plugging in. So 3. So that's negative t 3 cubed over 3. And then I plug in 3 again, so plus 3 squared over 3. And then I plug in the next batch, 6 times 3. Right. And then minus. For the next piece, I'll plug in 1. So 1 cubed over 3 plus 1 squared over 3 plus 6 times 1. Right. So that's the first piece. And then for the second piece, I have plug in 4. So that'll be 4 cubed over what? Over 3? Yeah, over 3. And then minus 4 squared over 2. And then minus 6 times 4. Right? And then minus, for the last part, you plug in the lower limit. So 3. So 3 cubed over 3. And then minus 3 squared over 2. And then minus what? 6 times 3. So you crunch all of this and you get, let me check. You're not going to waste time. So 61 over 6. Right? 61 over 6. So 61 over 6, and that's our answer. So I just showed you how you deal with what? Integrating an absolute value function. You first have to decide if you can split the interval to parts where the absolute value is negative and parts where it's positive. And then you can what? Eradicate the absolute values and then work on them. And that's all on 5.4. Please, any questions here? Is there any part you don't understand? So we learned, yeah. So is there any part you don't understand? Do feel free to interrupt. So we've learned how to, there's notation for for indefinite integrals. And then we looked at how to deal with absolute value, right? Integrals. And then we saw, what do you call it? We just saw that FTC part 2 is all that you'll be using, right? Whenever you want to find a definite integral, just get the antiderivative, evaluate at the upper limit minus evaluate at the lower limit, and that's all. Okay. Any questions? Okay. Then let me share the screen. Let's walk through this slide. Know that we're done with this, right? So split it up, get 61 over 6, which is 10.17 approximately. Okay, we have like a minute and some seconds. So let's get on to the next. At least I'll talk about the idea. And then the next time we meet, we just wrap up on Monday. So 5.5 is the substitution rule. The substitution rule. So for substitution rule, the whole idea is sometimes when you are finding either a definite integral or an indefinite integral, the antiderivative cannot be obtained directly, but you can assign, you can make a substitution so that everything will work out just fine, right? And this is connected to the chain rule, right? So for example, suppose you're asked to evaluate the indefinite integral 2x and the square root of 1 plus x squared dx. Then how do you do this? Right, this one says you introduce something extra. And what is that extra thing? or that extra thing is something you're going to see on Monday. So yeah, so thank you for your time. We wrap up on Monday. Yeah, I will see you on Monday. Yeah, that'll be the last meeting. So all the best. Enjoy the rest of your day and your weekend. I'll see you on Monday. You're welcome, guys.